Okay, in this problem, we have a cube that is expanding at a rate of 6 centimeters per second. So first of all, you have to, if you draw a picture here, I don't know if you know what a cube looks like, but you should come up with a picture like this, like a box. And, I'm recording this, so this is not going to come out perfect, but a cube is, each face of a cube is a square. That means each side will be equal. All right. Now it's asking how fast is the volume changing when each side or edge is 2 centimeters and 10 centimeters. So we're looking at two different answers here. And how fast is the volume changing? So that's a rate. That's a rate of change. And remember, in calculus, a rate of change is a derivative. All right. So what are they asking you to find? Well, first of all, we need a equation that connects volume with the edges of the cube. Now, the volume of any type of rectangular box, is V equals length times width times height. But in our problem, the length and the width and the height are the same because, it's a square. Now, in the textbook, if you looked at the solutions manual, they let each edge be equal to x. All right. Now, you could have used A, B, C. It doesn't matter. Just use a variable. You'll get the same results in the end. And so, if this edge is x, then also, all edges are equal. Right. So we're looking at that. So volume of a box would be length times width times height. So we're looking at x times x times x. Right. So that would end up to be x cubed. So that's the connection between volume and the edges of the cube. All right. Length times width times height will give you volume. Now, so that's our equation that we're going to be using. And let's find out what they're asking. How fast is volume changing? Okay. So therefore, they're asking you to find what? dV, how fast the volume is changing with respect to time. When what? Because this is variable rate of change. So when the when the edge, which is our x, is equal to 2 centimeters, and when x is equal to 10 centimeters. Okay, so that's what the problem is asking us to do. So we know that to find dV dt, we have to differentiate both sides of this equation with respect to time. All right, so that should be easy. When you differentiate this with respect to time, you're going to get dV dt equals, now differentiate this guy with respect to time. We're using the chain rule first. 3, put the 3 in front, subtract 1 from the exponent, you get 2 times the derivative of x with respect to t. So that should end up giving you dx dt. So this is our related rates equation right here. Now we should be able to find the volume when so and so. Now I didn't write down, we need to know we know what x is going to be. X is going to be 2 for the first problem. But what is dx dt? What does this derivative stand for in our problem? Well, I didn't write what was given to us in the problem. I forgot to write that down. So even if you forgot, that's fine. Because somehow, for us to find dV dt, we also need to know how the edges is changing with respect to time. Remember, x is your edge, right? But that was given to you in the problem. All edges of a cube are expanding here, right here, at a rate of 6 centimeters per second. So that was given to us. Edge, remember, edge was x, so therefore this rate of change, dx dt, was given to you initially in the problem, which was 6 centimeters. That came out bad, per second. Okay, therefore now you have that. We have a substitution for dx dt right here and a substitution for x, so therefore we're good to go. Now after that it just becomes elementary. So for the first one, when x is equal to 2 centimeters, well, dV, the rate of change of the volume, is going to be equal to 3, and you put 2 here for your x, so you're going to get 2 squared, which is 4, times dx dt, which in this case is 6. And you multiply all those guys out, you're going to get 3 times 4 is 12, 12 times 6, that's 72. And now, volume. Let's talk about the units. Our final unit, since we're talking about the change in volume, our units initially was given to us centimeters, so volume is units cubed, right? So we should have centimeters cubed, and our time factor was seconds, so this should be seconds. All right. So what do we know here? The volume is changing at a rate of 72 centimeters cubed per second when the edge is at 2 centimeters. Now that's going to change, of course, when the edge starts to become bigger. All right. When the edge becomes bigger, then this rate of change, the volume rate of change, will also increase. Okay, so that's not fixed. But anyway, the answer to the problem right here, for when the x is equal to 2, it's just simply this guy. All right, and then you repeat the same thing, of course, to find b, when x equals 10 centimeters. You just do pretty much the same thing that you did right here. You do your substitution. So instead of using 2 here for dx dt, you're just simply, no, sorry, instead of using 2 for x right here, you're simply using 10. All right, so you're going to end up with 3 times 10 squared, right, which is 100, times this is fixed all the time, 6. Okay, so then you end up with something even bigger. You're going to end up with 1,800 centimeters cubed per second. Okay, so as you can see, as the edge of the box gets bigger, right, this rate of change of the volume is even increasing even faster and faster over time. Okay, so very interesting. All right, so that's the answer for that, and hopefully you now understand how to do this problem. Okay, now let me see if I can get out of this here. I need to press